Okay, good evening, everyone, and welcome to the Chabot Space and Science Center virtual telescope viewing. And I hope everyone is having a nice weekend. I'm here with Gerald McKeegan and John Curry, and behind me is the star of our show, so to speak, Nellie, our 36-inch research reflecting telescope. And I'm Rich Ozer, and we have a nice program for you tonight. We do have some high clouds that we're dodging, so we're going to make the best of it. And we're going to get started by turning this over to Gerald, who has some announcements and requests for you.
All right. Well, yeah. As you saw on the slide before we started here, we are encouraging everyone to help support the Chabot Space and Science Center's virtual programming. We invite you to make a donation either on our Facebook page, or you can go to the Chabot Space and Science Center's webpage, chabotspace.org, and there's a donation button at the top of that page. We encourage you to help us out by making donations. Your donations help us continue to do the virtual programming during our pandemic shutdown when we can't open the museum itself. So anything you can do to help us out. And I wanted to let you know about another thing that we've got going between now and the end of the month. If you go to the Chabot Space and Science Center website and sign up for a membership, you'll see a membership link on the website. If you sign up for a membership between now and the end of the month, Chabot will automatically make a member out of one of our local teachers. So it's a kind of a joint thing where you become a member and the teacher becomes a member automatically at the same time. So we encourage you to do that and help us out. So I think we'll go ahead and get our program started. I think we're going to start with the planet Mars.
Yes, we are. Let me share my screen here.
Hopefully the clouds aren't causing us too much trouble.
No, it's not so bad.
Oh, there it is. Oh, yeah, I can see some detail.
Yeah.
Indeed. In fact, I see the slightest hint of a white ice cap down there at 7 o'clock. Yeah,
right over there.
Right there.
I have to chase it around the screen. It's swimming.
Yeah. So as Richard said, we have a little bit of cloudiness tonight and a little bit of turbulence in the sky. We're on the back end of a weak front that passed over the Bay Area earlier today. Fortunately, there are nice clear skies behind it, but we're still getting the remnants of that front. And so it's going to make our atmosphere a little turbulent. And that's going to mean our images are going to go in and out of focus. But you see Mars there. Mars is the fourth planet from the sun. It's about half the diameter of the Earth. And we call it the red planet, although as you can see, it's more of an orange planet than a red planet. You see dark features at the bottom half of the planet. That's the southern part of Mars, which is an older, more rocky part of the planet. You'll find a lot more craters there, a lot more mountains and so forth. Whereas in the northern half of the planet, it's a lot smoother. It's more desert-like. And we think that that's because a long time ago when Mars had active volcanoes, most of them were in the northern half of the planet. And those volcanoes spewed out gas and dust, and a lot of that dust settled out and formed those big, huge, light-colored desert areas. So when you go there, you don't see as many craters and you don't see as much mountainous terrain and so forth. So it's a lot smoother and brighter in color. A couple of interesting things about Mars. If you like sleeping in, you want to go to Mars. Yeah, so a day on Mars is 39 minutes longer than a day on Earth. So, if you like sleeping in, you can go to Mars. You sleep in 39 minutes every day and you still have a 24-hour day in front of you. So that's pretty cool.
A good piece of trivia related to that. The Spirit and Opportunity teams. Those are the pair of landers and rovers that went to Mars several years back. Everybody on the control team for those missions got a special watch that was a 23-hour watch. So that way they had to synchronize their day and sleep cycle with
Actually,
the
actually,
yeah.
yeah, actually, it was a 24-hour and 39-minute watch. Yeah,
Oh.
the watch was made by Executive Jewelers. They went to a major watch manufacturers like Bulova and Speidel and all those guys, and none of them wanted anything to do with it. So they got hold of a local jeweler in Pasadena and threw the idea at him, and he said, I think I can do that. And so he took some watches, I think they were Speidel watches, and he changed the watch works to run.
I guess he had to put a different gear in, main gear.
Yeah. I'm not sure how he did it, but he was able to get a whole bunch of them. He made 200 of them, and I own one.
Do you really?
I do.
Well, you need to bring it in and show everybody next time.
Right. Yeah.
Especially me.
Yeah. So they issued them to all of the Mars rover crews so that they could live on a 24-hour and 39-minute day, which actually was not much fun because you were constantly shifting relative to Earth Day. And so, you start out working on what seemed like almost a normal, day-night schedule. And then pretty soon you were half day and half night. And, they had a rough time with that. But
it really messed up people's circadian rhythms, I'm sure.
Yeah. So of course, that's the good part about living on Mars. The bad part is the air is almost non-existent. It has no oxygen, or it has hardly any oxygen in it, and it's freezing cold. So there's pluses and minuses. The atmospheric pressure at the surface of Mars is 1/100th the atmospheric pressure at sea level here on Earth. So if you walked outside, it would feel pretty much like a vacuum. And like I say, the temperature is very cold. Most of the time, it's well below zero. Once in a while, Mars does have seasons like the Earth. And once in a while, in the summertime, you get temperatures up around maybe 50 or 60 degrees Fahrenheit, but that's only for a brief period during the day. And the problem with it is because the atmosphere is so thin, your feet might be at 50 degrees Fahrenheit, but your head will be at about 10 degrees below zero. So, there's a huge temperature gradient just going up a few feet. So
it also has legendary dust storms.
Oh, yes.
So when the temperature starts to change on Mars, there are dust storms that sometimes cover the entire planet. You can't see any features at all for, weeks and weeks on end. And the dust storms, though, are not dramatic in the way that the movie The Martian showed them.
No.
It's not really high winds that are going to knock over the radio towers and dishes and everything. It's more like kind of like a gentle dust that just comes up from the ground and covers everything.
Yeah. If you read the book The Martian, on page 3, they describe the windstorm that they're going through, and they describe the velocity of the wind as 175 kilometers per hour, which sounds pretty forceful. I mean, that's faster than the worst hurricane we have. However, because the air is so thin, that 175 kilometer per hour wind has very little force.
Yeah.
And I did the math once, and it equates to a breeze here on Earth of about 12 miles per hour. So So they got that part wrong, and what was his name?
It made for great drama in the movie,
Right,
though.
right,
It would
right,
have
right.
been, it would have been very hard to make a crisis out of a 12-mile-an-hour wind.
Right.
All right.
Yeah.
Okay. So, if there are any questions about Mars, otherwise, I think we could move on.
Well, since we're on Mars, do you want me to? I'd like to show something really quick, if you don't
okay.
mind.
Yeah, sure.
Let me share the screen to my local. Whoops. Here we go. And I will go here.
While you're doing that, somebody asked if it's water, ice, or some other chemical on the poles, and the answer is yes. It's actually mostly carbon dioxide ice, but there is also
some water.
Water ice as well. Yes.
Okay.
He also asks if any landers have gone to the poles.
Yes, we did have one lander that landed near the poles. They deliberately landed on an area where there had been ice previously, but there was no ice when they landed there. They deliberately chose to do that because they wanted to see if there was still ice below the surface. And when they landed, the spacecraft used thrusters to gently land on the surface. Those thrusters blew the dirt off to the side and exposed a layer of ice inches below the surface. So they accomplished their mission as soon as they landed. So.
All right. Well, what I'm showing you here, you noticed when we were looking at Mars Live, there were dark areas, particularly on the lower left quadrant of the planet. And this gives you kind of a much sharper view of what those dark areas look like. This is a series of video images that have been stacked and assembled to create a GIF file. This was done by a member of the Chabot board named Dan van der Zanden. He's also an EAS member and a Mount Diablo Astronomical Society member. And he has done a fantastic job photographing Mars here. This is really getting into territory that I've only seen a handful of people accomplish with the sharpness of this image.
Yeah, Damien Peach, Christopher Go,
and now Dan van der Zanden.
Yeah, very small club.
Yeah, it's a small club, and I was really impressed when this came across my email today, and I immediately wrote him and said, "Can we use this tonight?" And he graciously accepted. So anyway, I wanted to call him out on this and let everybody know that we've got a fantastic video astrophotographer in our midst.
Right. Now, you may wonder, why is it that we don't see it like this when we're looking with our telescope live here? Doing this actually takes a lot of work. You shoot video over long periods of time, and then you go through frame by frame, picking out the best frames, and you use those to piece it together to produce the final video.
You might pick here. Yeah, you might pick out dozens of frames just to make one video frame. So it's like you'll end up with hours and hours of video, and you'll be teasing it apart, picking the good frames, stacking the good frames, and that's just one moment in the overall GIF image. And then you have to repeat it for every aspect of the rotation that you're seeing here. So he put a lot of work into this.
Somebody asked a question, and I want to answer it because, I know it is a concern for some people. The question is, are we in the same place? Yes, but we are in the same observatory building, but Richard and I are on opposite sides of the telescope. Yep. And so we are, good 12
I'd say about 20 feet away.
Yeah. We're pretty far apart. Plus we have the roof open. So we're outside. Our observatory is a rollback roof observatory. So it's not a dome. We roll the roof all the way back, so we're completely exposed to the night sky. So we are well separated from each other, and we are facing in the opposite direction. So we've taken a lot of precautions here to make sure we're safe. And then John, he's so far away, he's at home.
I'm 30 miles away, sitting on my couch at home.
Yeah. So yeah, we're being safe.
Usually I do go up there, but tonight is a different story.
Yeah, we are very conscious about COVID safety and so on. So we're good.
Thank you for asking.
Yes. Yeah. Well,
What's next?
I was thinking we would give a try. Looking at the sky here, it looks like it's actually not too bad there.
Yeah.
So let me
agreed.
see if we can go to a galaxy. We're gonna have to do a long exposure, but we're gonna
Yep.
go.
Let's do a midway star to
Okay, it's
set the
actually
scope.
M77 is not too far from Mars. So if
All
you're
right. Well,
centered on Mars,
we're not exactly centered. Let's.
why don't you go ahead and center it up, and I'll sync it.
Yeah.
In the meantime, Steve wants to know, is the ice covering the pole smooth or cratered along with crevices and such?
No, there's a spacecraft orbiting Mars right now. It's called a Mars Reconnaissance Orbiter, or MRO. And if you go to their website, they have tons of images taken of all over Mars, including the polar ice caps. And you will see what the ice caps look like. It's very rough terrain. And so it's definitely not nice, smooth ice. Although when that lander landed, on the surface and blew all the dust away, the ice underneath was actually pretty smooth, but that was a very small area that they were looking at.
But the landers won't be doing any ice skating up there.
No.
Yeah.
Okay, we ready, Richard?
Yeah, we're ready. Go ahead and sync, and then we can get on to
Okay.
M77.
Okay, so what we're going to do here, we're going to slew to a galaxy. You won't see it right away. Richard's going to have to take maybe a 30-second or 45-second exposure to see it. This object is at magnitude 8.8. So bear with us for a few seconds, and I'll tell you why it is that we are looking at this. For one thing, it's relatively high up in the sky, so it's a good target to look at. But I've been working with a production company, a TV production company that's producing a documentary for the Discovery Channel. And the topic of their documentary is the work done by Edwin Hubble back in the 1920s to figure out that the universe is expanding. And what Edmund Hubble did was to look at a total of 46 galaxies, measuring their distance using Cepheid variables, and measuring their redshift or blue shift. Now, you may have heard the term redshift, and let me explain what goes on. When you point a telescope at a star, there it is. Yeah.
Oh, good.
When you point a telescope at a star and run the light from that star through a prism or a diffraction grating, you get what looks like a rainbow. But within that rainbow, you'll see dark lines, which are the absorption lines and caused by the different elements within the star's composition. And those absorption lines can shift around. If you do the same experiment in a laboratory and look at the sort of static position of those absorption lines, that's the normal way you would analyze, what's the composition of a gas or some material that's been heated. But when you look at a star, if that star is moving toward you, all of those lines will shift toward the blue part of the spectrum. If the star is moving away from you, all of the lines shift toward the red part of the spectrum. So if a star is moving away from you, we say its spectrum is red shifted. Now, when Hubble did this experiment with all these different galaxies, he expected that some would be moving toward and some would be moving away, and that would be pretty much random. but in fact, he found that most of them were moving away from us. And he tried to account for this. You know, he tried to correct for the motion of our solar system through our galaxy and so forth. No matter what he did, he still found that most of these galaxies were moving away from us, not toward us. And that sort of confirmed what Einstein had theorized a few years earlier, that the universe was expanding. So anyway, the production company is doing a documentary about that episode, and they have asked that we point our telescope at some of the galaxies in Hubble's list so they could use it in the video. Unfortunately, just as they were about to come up here for our production, they were actually going to be up here later on this week. The Bay Area counties decided to shut us all down. So we're going to have to wait till later on in the year. But I had already made a list of galaxies that we could see that were on Hubble's list, and this was one of them. So I thought, great galaxy to look at.
Gerald, so, how far is M77?
It's about 60 million light years away. So it appears sort of small in our field of view, but probably if you did a little bit longer exposure, you'd capture a lot more detail. And it's a spiral galaxy, very common type of spiral galaxy. And it is, in fact, moving away from us. I forget what the velocity was, but it's definitely several hundred kilometers per second moving away from us here in the Milky Way. And that's true of most of the galaxies that we see in the night sky. They are moving away from us because of the expansion of the universe. You doing another exposure?
Yeah, let's just do
it. Okay. Okay. Yeah. Yeah.
So we were talking about this a little bit earlier. So Hubble did a lot of this work right here in California at the Mount Wilson Observatory. Using, I knew that he used the 60-inch there quite a bit, but Gerald, you let me know also that he made ample use of the 100-inch as well.
Yeah, and he continued doing this. He wrote a very famous paper in 1929 where he summarized all this work. And you know, they were trying to figure out, you know, how can they write an equation for you know, how fast something's moving away, or how far or how fast. What the relationship is between how far away it is and how fast it was moving. And, you know, one of the things they found was the farther away a galaxy is, the faster it's moving away from us. And there's a reason why that happens.
Oh, yeah, there we go. That's nice.
And he tried to write an equation for it, and he found that he had to plug in a fudge factor, which became known as the Hubble Constant. And at the time, he thought it was something like 500 kilometers per second per megaparsec. A megaparsec is a very long distance in astronomy, and that number has been modified several times, but it is still being used. I think the number is now down to something like 70 or 71 kilometers per second per megaparsec. And what that means is if something is 1 megaparsec away, 1 million parsecs away, it's going to be moving away from us at 70 kilometers per second. If it's 2 million parsecs away, it's going to be moving away from us at 140 kilometers per second.
And so of course, that's how it relates back to the redshift, because for every you know increment of speed that it's moving away from us, there is an equivalent increment in the redshift of the spectrum. So when we look at a galaxy and we measure that redshift, we're able to figure out how fast it's moving away from us, and then using Hubble's constant, determine exactly, not exactly, but roughly what the distance is. And I hope that answers Steve's question.
Yeah, now somebody asked, how do you know it's 16 million? Actually, 60 million light years away. And again, that's the Cepheid variables. There are several different, what we call standard candles. Cepheid variables are one of them. A Cepheid variable is a star that changes brightness in a regular pattern It dims very slowly, and then it very rapidly brightens again, and it does this in a repeating cycle. And the amount of time between going from dim to bright and then back to dim again, that time is directly related to the luminosity of the star, how bright it is. And by using that information, you can calculate how far a Cepheid variable is away from it by looking at the period of its cycle, and estimating from that how bright it should be. If it was a standard distance away, then you measure how bright you actually see it, and then you calculate the distance from that. So that's one of the techniques. Another standard candle that we use is type 1a supernovae, which also follow a very consistent pattern. And so those are the techniques that we typically use.
And
these
go
ahead.
I'm sorry. These are estimates, and they are fairly rough estimates.
Yep.
Right.
In fact, NASA's site says that M77 is 45 million light years away. So there can be quite a
every few years, there's a re-estimation of the Hubble constant. There's a re-estimation on what it means to have a standard candle. They shift the age of the universe by a couple of million, or a couple billion years, one way or the other. And so it's always a moving target. But those standard candles are how distance and redshift have been calibrated. So if you have a standard candle go off in a distant galaxy, and you can also measure a redshift, it gives you a lot of information.
Right. And again, because there is an equation that relates redshift to distance, that's another technique that you can use to measure the distance. Of course, you have to know the correct Hubble constant, and we're still we got it pretty close, but we still are tweaking it a little bit. And every once in a while, somebody comes up with a new number, and lots of arguing about what is the correct number and so on. But we've gone to from 500 to somewhere between 68 and 72. So we narrowed it down a lot.
That extra 10 seconds gave us a lot of extra detail on this. You can see that we got spiral arms going all the way out to here.
Right.
And you can see a little blob right here where the cursor is, and I'll move it away now. And that's what's called a hydrogen alpha region of the galaxy, where there's a lot of star formation. And you can see a lot of structure here in the core area of the galaxy as well. And as Gerald said, we got some color as well. So this came out great.
Yeah. Now you're probably looking at this and saying, "Well, that's not a very good image," but
I think it's great.
We're looking at it. We're saying it's a great image. But what you got to understand is, to make this look really good, Richard would have to take dozens of similar photographs.
5 to 10 minute exposures for hours. And then stack them up and process them. But man, for a 45-second shot or 55-second shot, this is really as good as you can ask for.
That's pretty cool. All right.
Yep.
Well, let's see. Any other questions here? Somebody wants to know.
How does gas and dust make a spiral galaxy? There's a good one for you.
Okay. Well. Galaxies are actually formed from huge clouds of gas and dust, and most of this happened a long time ago. And these clouds, even though it's just gas and dust, each individual atom and molecule has a gravitational field. And so you combine the gravitational fields of all this gas and dust, and it slowly wants to pull itself together out in space. And as the cloud of gas and dust condenses, it starts forming stars. And you get more and more star formation going on. And if you get enough stars, the whole thing starts to rotate a little bit because, it's not all falling inward at the same speed or in the same direction. And eventually some direction tends to dominate the rest of them. And then you start getting rotation of the cloud and it continues to condense. And you get more and more stars forming. And eventually you've got a galaxy, especially if you end up with a black hole at the center. So most galaxies, I think probably all galaxies have black holes at the center. All right.
All right, let's wait.
Let's see. Somebody said, aside from the Andromeda galaxy or any other galaxies or stars moving toward the Earth. Well, yes. In our own galaxy, within the Milky Way galaxy, we have a lot of stars moving both toward and away from us because of their relative motion. The sun is orbiting around the center of the galaxy. It takes about 230 million years for us to orbit around the galaxy. Some of the stars are orbiting slower, some are orbiting faster, and there are stars that are actually moving in weird directions. They don't all orbit in the same direction around the galaxy, and that is actually due to the fact that the Milky Way has sometimes sucked up other galaxies. And Richard, I think you had something about a recent discovery of the remnant of a galaxy, or maybe it was a dwarf galaxy.
Let me go to that screen. Give me a sec here to bring that up.
In the meantime, Laura asks, is that a planet to the left? No, that's a star.
Yeah, probably a foreground star.
A star in our galaxy close to us.
Because of the seeing tonight. So everything is moving around, so it's filling up a big circle. All right, let me bring up my screen here.
So the thing that we know about the Milky Way is that over the last 10, 11 billion years, it has occasionally sucked up smaller galaxies in its vicinity. And so the Milky Way is really made up of other smaller galaxies. In fact, there are two dwarf galaxies outside the Milky Way right now, the Large and Small Magellanic Clouds. They are slowly being drawn in towards the Milky Way as well. But I guess, Richard, you discovered, recently discovered something?
What astronomers are frequently discovering, when I say frequently, every several years there's another story like this that comes up, is the remnant of some ancient collision between the Milky Way galaxy and some other galaxy that was in our local group. And the Milky Way is a very sizable galaxy, and when smaller galaxies get too close, the gravitational attraction of the Milky Way will overwhelm the stars in that colliding galaxy, and they may remain with the Milky Way for the rest of their existence. And so what astronomers have found is a fossil galaxy in the center of the Milky Way, and this area is what's left of this fossil galaxy. And the way they know that this collision had occurred is if they look at thousands and thousands of stars in that region of the sky, and they notice that there is a significant number of them moving in a different direction and a different speed than the bulk of the stars in that part of the Milky Way galaxy, then they know it's the remnant of some sort of collision. And that's in fact what they found. There's no way to point a telescope at this and say, there's the remnant of that galaxy. You have to study the motion of individual stars, and only, I'd say only recently in the last decade do we have the instrumentation to do that really effectively and quickly. And that's the result. There is another related photograph.
And this image is not a photograph, really. Obviously.
Yeah, I should say artist conception.
An artist rendition.
Yeah, let me stop that share and share the other one.
We don't have any spacecraft away from the galaxy.
And you can see that it's oblique to the Milky Way, right? The axis of this fossil galaxy is perpendicular.
Yeah.
Okay.
So as Richard mentioned, these stars are moving in a strange direction. They're not moving the way the bulk of the the stars in our Milky Way move. If you ever want to see an example of this, in the summertime, there is a bright star that is high up in the sky. It's called Arcturus. And Arcturus is actually a star that was part of either another galaxy or perhaps another dwarf galaxy that was sucked up by the Milky Way sometime in the past. And it is going in a completely different direction than all the other stars around us. And it's a nice bright star that you can easily see in the night sky. But you want to look now because it is moving so fast and in such an odd direction that 1,000 years from now, it won't be there anymore. So it's one of the fastest moving stars in our night sky in terms of motion across the sky over time. So, and it's the same idea.
Yep, captured by some ancient collision.
All right.
Well, it's really clouding up, so maybe we ought to satisfy. A bunch of people have asked about the upcoming conjunction.
Oh yeah.
And maybe I'll turn it over to you to talk about that, because some people are calling it a conjunction and other people are calling it a Christmas star.
Yeah.
And I think we need to really work this out and solve it tonight.
Yeah, I did a I did a TV interview earlier today, and they contacted me and they said they wanted to talk about the Christmas star, and I'm going, what are you talking about, Christmas star? and I realized they were talking about this upcoming conjunction of Jupiter and Saturn. So I'm going to share my screen here in a second and show you some images. Jupiter and Saturn are both in the sky right now, and if you go out and look very low in the western sky right now, you would see them. They're very close together. And this is a diagram that shows what has been happening over the last couple of months. Over that time, Jupiter and Saturn have been getting closer and closer together. Now, the reason for this is Saturn is farther from the sun than Jupiter, so Jupiter orbits the sun faster than Saturn, so they've been catching up to each other. At the same time, the Earth has been going around the sun and it's been changing its position, so both stars have been farther and farther towards the western sky each night, but they've been getting closer and closer together. On December 30 or 21st, which is the first day of winter and only 4 days before Christmas, the two stars will be so close to, or two planets will be so close together in the night sky that they will appear almost like one star. Not quite one star. If you've got not very good vision, they'll look like one star. If you've got sharp vision, you might be able to see that there's actually two planets there, two stars in the sky. They're going to look very close together. In fact, I've got an image here. Let me see. There you go. So on the 21st, about 30 minutes after sunset, if you look to the southwest, just above the horizon, you'll see some regular stars in the sky, and then you'll see this fuzzy thing that looks like it's an elongated star or something like that. And that's actually Jupiter and Saturn so close together that they've almost merged. Now, they're not really that close together. In fact, at that time, they'll be about 455 million miles apart, but they'll be along the same line of sight for us, and that's why they appear to be merging. Now, if you put a telescope on it, or even a pair of binoculars or a small telescope, you'll be able to see both planets in the same field of view. Jupiter and Saturn, even in our telescope here, which has a pretty small field of view, you'll still be able to see both planets in the same field of view. They'll be oriented roughly the way you see here. This is an animation. It's not the actual image. We have to wait until December 21st to take this image. And
what you should do, by the way, is not wait until December 21st. Observe this a few times leading up to that.
Yeah, dude. So really, you really appreciate the fact that they're moving closer and closer together. So
yeah, the other thing to be aware of is that this is happening very early in the evening. So you want to be outside at like 5:30 in the afternoon to catch this, because if you wait to 8 or 9, they're already going to be set.
Right.
So
right,
yeah,
right,
it's
yeah.
going to be, that's after sunset. The sunset's at around 4:30. So it's an hour after sunset, and you should be able to see them just fine.
Yeah.
Also, at this time of year, we have no idea what the weather is going to be doing.
Right.
So you might not see anything at all.
You might not see anything.
Try
right.
to observe it earlier.
So, astronomers all over the world are going to be checking this out and taking photographs. You'll see lots of photos, I'm sure.
It'll be all over the internet. But what I do want to say is I want to show you something that is going around on the internet, and it is not what this will look like. Hold on for a second.
Let me show one more image.
Oh, go for it. Yeah.
I just want to explain why this is happening.
Oh, sure.
So here's an image of
good.
the solar system looking down on the solar system, and you see Jupiter in its orbit around the sun here, and here's Saturn in its orbit around the sun here. Here's the Earth down here. All right, so you see that they're all lined up. So that makes the two planets appear to be merging. And you notice that line of sight is very close to the sun. That's why you have to look right after sunset, like 30 minutes or so after sunset to see them. And if you wait any longer than that, they're going to go down below the horizon. But this is why it's happening. Now, this happens about every 20 years that Jupiter laps Saturn. Jupiter takes 12 years to orbit the sun. Saturn takes about 30 years to orbit the sun. About every 12 years from our perspective here on Earth, you see the two pass close to each other. But this one is unusual. Most of the time they pass close, but they're not really appearing to merge. They're just very close in the sky. But to have them get this close together, that's pretty unusual. The distance between them on the sky will be 1/5 the diameter of the full moon. So it's a very small distance. Some of you may be familiar with the stars Alcor and Mizar, which is in the Big Dipper. And if you got really good eyesight, you'll see that Alcor and Mizar are actually two stars separated by each other. The distance between them is 11.5 arc minutes. The distance between Jupiter and Saturn on our sky will be 6 arc minutes, so less than the separation between Alcor and Mizar. So they're going to be pretty close together. This happened once before at Christmas time, almost 800 years ago, in the year 1265 by our calendar. They had a similar close conjunction of Jupiter and Saturn, very close to Christmas time then. So, the media is calling this the Christmas star. I even had somebody say it's the Star of Bethlehem. I'm not sure about that. It's just a really cool conjunction of two planets close to the horizon near Christmas time.
Hold that thought, because this is what's going around in social media. I saw this the other day and immediately commented on it. This is the picture that's accompanying the announcement that on the 21st Jupiter and Saturn will merge into one star, and this is the picture that's going around. It will not look anything like this. I guarantee it.
Not at all.
Yeah.
Wrong color, wrong brightness.
Yeah. Fake news.
Yeah. All right. Yeah. So, I'm kind of keeping an eye on the clouds here.
They're getting.
Yeah, we're not going to be able to do anything more. Yeah. We were hoping to show you the Orion Nebula. The constellation of Orion is up, and there is a bright nebula in the Sword of Orion that's really cool to see in the telescope. But right now, there's a whole lot of clouds in that direction.
Yeah, totally obscured by clouds. Yep.
However, once again, we can cheat here. And I can show you, I think.
We have photographs.
We have photos, I think.
Yes.
Hang on here. Yeah, okay, here we go. So I've got a couple of images here. I'm going to share the screen here. So there's two images. We have the main telescope, which has a
Oh,
relatively
nice.
small field of view. This is an image taken. It was just a quick snapshot that we took. And you see the Orion Nebula, all this cloudiness around here. That's the nebula. It's gas and dust condensing to form new stars. And so many of the stars that you see here are very young stars that have emerged from the nebula. These 4 stars, there's actually 6 of them in here, but it looks like just 4, we call the Trapezium. And the Trapezium are stars that are very massive, extremely hot, emitting a lot of energy as ultraviolet radiation. And 2 things are happening. First of all, that radiation is actually pushing the cloud away from the stars. So you see a kind of a pocket within the cloud here where the gas has been pushed away from those stars. But they're also emitting ultraviolet radiation, which goes out and hits the cloud and ionizes the gas in the cloud and causes it to glow. So some of what you're seeing is reflected light, and some of it is actually light emitted by the cloud itself. It is kind of hard to take pictures of this object because those stars are so bright that if you expose long enough to see all the cloudiness, there's much more cloudiness than what you see in this image. If you expose long enough to see all that cloudiness, you end up with this just being a blob. And one of the things we did with this telescope, I got to find it here. Yeah, maybe right here. There it is. So one of the things we did, we have a finder scope on our main telescope. A finder scope is a smaller telescope with a wider field of view. And so one night I put the camera on the finder scope and took a picture. You see much more of the cloudiness here, but I exposed it long enough to where we got all the cloudiness. And you see that where the trapezium is, it's just a big blob there. There's just so much light coming from those trapezium stars. It just washes out the center of the nebula. So these are images taken. Sometime here in the next few weeks, we will actually try to put the telescope on the Orion Nebula, and you can see live images of that. Unfortunately, Mother Nature is not cooperating with us tonight, but this is what you would see. All right.
Stephen asks, so the stars in the trapezium orbiting each other, or are there distance?
They are not orbiting each other, but they are moving together through space. So they are not orbiting each other. Although,
hold on for a second, Gerald. Yeah, there we go. Sorry, there was a break in the feed there.
Oh, okay.
The internet connection up here is acting up a little bit.
Oh.
All right, so you might want to repeat that.
I didn't notice it at all from here, but good.
Yeah.
Really?
Yeah.
Okay. Well.
Okay.
But the 2 double stars that are in the trapezium, you mentioned
right.
6.
Yeah.
Those are in orbit around each other.
Right. Yeah. So there's 4 really bright stars, but there are 2 other stars that are much dimmer, and they are orbiting around 2 of the bright stars. One of the things that we do when we're looking through the telescope and we're trying to assess how good the viewing conditions are, you'll often hear us talk about whether it's a 4-star night, a 5-star night, or a 6-star night. And what we're doing is trying to see how well we can see all 6 of those stars. We can see the 4 easily, but if we have good viewing conditions, we are likely to see a 5th. And if it's really good, we'll see all 6 of those stars. So if you're ever up here back, or when we get back to normal operations, we can actually have you come up and look through our telescope. If you hear us talking about a 5-star night or a 6-star night, we're talking about how well we can see through the telescope.
I thought it was the rating on Yelp.
No. Long before the internet came along, we were using a star system for assessing quality.
If we happen to be looking at the Orion Nebula.
Right. So
another question, do constellations change since the universe is expanding? Well, yeah, they do, but over a very long period of time.
Right. Like thousands of years.
And constellations are stars all in our galaxy. So regardless of what the universe is doing, the galaxy is moving.
Yes.
And that's causing the stars to.
Yeah, if you ever want to have
the constellations don't change shape because of the expansion of the universe. They're changing shape because all the stars that we see in the Milky Way that form those constellations are orbiting the center of the Milky Way at different rates, and that the perspective from our location is constantly changing. So over time, the shape of those constellations change.
Right.
That's exactly. It does take thousands of years, though.
Right.
Yes.
Really
it's not going to be from week to week.
Right. One of the things that sometimes confuses people is we talk about the stars within our galaxy as orbiting around the galaxy, and not moving away or toward us because of the expansion of the universe. And one of the things you have to understand is the expansion of the universe is a big picture experience. Gravity is actually stronger than the expansion of the universe when things are close enough to each other. So the stars in the galaxy are dominated by gravity, by the mutual gravitation of the stars in the galaxy. But galaxies, there's billions of galaxies out there in the universe, and there's huge spaces between them. And so on that big picture level, that's where the expansion of the universe is actually carrying galaxies away from us. So it doesn't do it to the stars in our galaxy. It does do it to other galaxies that are far away from us. And one of the interesting things you can do, if you happen to have the right software, there are several different planetarium packages that you can get out there. And quite a few of them will actually show you what the changes to the star positions would be like in the future. So you go to the planetarium software and you say, okay, I want to see what the night sky will look like 1,000 years from now. You set the date in the software, and it repositions the stars so you can see what the constellations will look like in 1,000 years. And you'll actually see that the stars change position. All right.
Nice. Mm-hmm.
What other questions we have here? We're pretty much losing our sky here, so I don't think we're going to be able to point our telescope at anything else here.
Okay. Wasn't there a recent discovery by an orbiting telescope of 1 million previously unknown galaxies? Well, they are discovering lots of galaxies all the time. I don't know how recent we're talking about here.
Is that the Hubble Deep Field behind you, John?
No, that's
that's
M56. As a matter of fact,
it's a globular star cluster. Yeah. So if you search on the internet for the Hubble Deep Field, that's what it's called. It's a photograph, and they've actually done it a couple times now. Photograph taken by the Hubble Space Telescope, and what they did was point the telescope at a region in the sky where there was not too much going on. There weren't very many stars. There weren't very many galaxies. And then they exposed for a long period of time. I think it was 36 hours. And they just opened the shutter and let the light come in to see what they would see. And the result was a photograph of thousands of galaxies. In the photograph, the original one, there are only 4 distinct stars where you see individual stars. Everything else you see in the photograph is galaxies. Thousands of galaxies in this one image, which was taken of a very small portion of the sky. And we know that pattern is replicated across the whole sky. So if you imagine just one picture showing thousands of galaxies, if we then shifted the camera just a little bit, took another picture of the same size of the next region over, and keep doing that across the whole sky, everywhere we look, we just see thousands and thousands of galaxies, and we're only seeing a small percentage of the total universe. So
I have a picture of that up I could share real quick.
Okay. Yeah, great.
That was a great description of it. But picture's worth 1,000 words.
Yeah.
And this is a kind of a more of a thumbnail sized one. I didn't have time to dig around for a full size one. But everything you see in this image, every dot that isn't just black space is a galaxy. These are not stars.
And if you blow it up, there's actually really faint ones in there that you don't see very well in this image, but
yeah,
it's just thousands of, and this is just a tiny little patch of the sky, and it would be the same no matter what direction you look.
We're talking about like the size of a pea held at arm's length,
right?
Like or even smaller.
Looks like you can download a 3.4 megabyte version.
Yeah, you can.
Then you can see some really small galaxies.
That would certainly cut off our video and voice.
Yeah. All right. Well, let's see. Are there any other questions that folks like to ask? Apologize for not being able to do much with the telescope right now, but the clouds are moving in here.
Is the detection of methane on Mars a possible sign of life there? Well,
it depends on who you talk to.
Yeah, it's 50-50, right?
If you talk to Chris McKay, he's adamant that means that there's life there. Chris McKay is a scientist. He's a very well-known scientist down at Ames Research Center, NASA's Ames Research Center, and he is very much convinced that the methane that they occasionally detect on Mars is a sign of life. The way the chemistry works, if some natural process generated some methane, it should rapidly dissipate. But since we keep seeing it over and over again, there has to be some process that continues to keep generating the methane. And the only process that we know that for sure does that is life. So that's his argument. Others say no, there are other natural processes that could also account for it. So the debate is still on, but it's up to you. And Chris McKay, he's very much convinced that there is life out there on Mars and elsewhere in the universe. And anytime he finds evidence for it, he's going to really talk it up.
Okay. Would the galaxies in the Hubble Deep Field be existing today because of their age? Well, most
of them are probably still there. The galaxies, our galaxy is almost as old. Our Milky Way galaxy is almost as old as the
known universe.
Right. We're almost 12 billion years old. So we've been around pretty long time ourselves. So yes, those other galaxies are very old. But one thing you got to keep in mind, when you look back at a galaxy that's, say, 10 billion light years away, you're looking back in time 10 billion years, and the galaxy was a lot smaller 10 billion years ago. So what we see where that galaxy is today is actually much farther away than what we see it when we look at these images. So you got to keep that in mind. Let's see, I see a question from Lynn Brechtel up there. I think Lynn's up in Oregon or Washington now. I can't remember which. She says, we might explain how it is that the Hubble can keep pointing at the same part of the sky for 12 hours or 36 hours. Yeah. So what they do, they have gyroscopes on the Hubble Space Telescope, and they just set the telescope so that as it's orbiting around the Earth, it is slowly orbiting or rotating to compensate for its change in position as it goes around the Earth. So it continues to point at the same part of the sky for long periods of time. Now, they're having to get a little more creative in doing that because a couple of the gyroscopes on the Hubble have failed, and there are no new repair missions planned. So they've got to make do with what they got. But that's basically how they do it. They also use gravity gradient, which is if you have something at an angle orbiting around the Earth, the part that's closer will get pulled a little bit more than the part that's farther away. That's called a gravity gradient. And there are some other processes that you can use to keep the telescope pointed where you want it to point.
Alan Roach says there's Mexican restaurants on Mars, and that's why there's methane there, I guess.
Okay. All right.
A little space humor.
Yeah, really. Very little. All right. Well, we're coming up to on our 10 o'clock limit here. We do have to shut down at 10 o'clock under the new rules. So we'll catch any last minute questions and then call it a night here. Little VS, besides spiral galaxies, what are the other types of galaxies? Good question.
Yeah.
The most of the galaxies that you see are called spiral galaxies. There are galaxies called elliptical galaxies, and an elliptical galaxy can look like anything from a ball, a round ball, to a football shape, American football shape. And those are called elliptical galaxies. And then there are galaxies called irregular galaxies, and they don't really have a symmetrical shape to them. They're just irregular. So those are the three general classes of galaxies. Within those, there are subclasses depending on how many spiral arms there are, how many times the spiral arms wrap around the galaxy, whether they come out from the center and the central region is round, or if the central region is a barred galaxy, like our Milky Way is a barred galaxy. Those are all subcategories of galaxies. So, but the three main classes are spiral, elliptical, and irregular.
You left one out.
Yep. What?
Lenticular.
Oh, yes. Okay.
Those are the ones that are in between spiral and elliptical.
Elliptical, yes. Yeah. All right. Okay. Any other questions other than?
Yeah, we got lots of thank yous.
Okay.
Yeah. Well, if we didn't get to your question, keep it in mind and ask it next time. We'll try again.
Yeah. Now I have to.
Oh yeah, somebody asked who's sad about Arecibo here. Well, I did have something on Arecibo. If you want to take a few minutes.
Why don't you pull that up, and while you do that, let me just announce one other thing here.
Oh, go for it.
As most of you know, or a lot of you should know, the Bay Area, starting tomorrow night, will be in a mandatory stay-at-home situation. And we are not sure whether or not we're going to be able to continue doing this. We think so, but we're still waiting to get the official answer from the Alameda County Health Department. So it's possible that we may have to wait until this new shutdown is over. It's supposed to end on January 4th. And we'll just try to keep you informed on the Chabot website to let you know whether or not we will be able to continue doing this.
Yeah, go ahead and tune in. Assume we're going to be here, and there'll be an announcement.
What we may end up doing is doing the show, but instead of putting a camera on the telescope, we'll do it from home. We'll show you images taken with this telescope. We'll figure something out here. So we just may not be able to come up here and put the camera on the telescope. So.
Right.
All right.
All right. So somebody mentioned, who was it who mentioned that? Who's sad about Arecibo? Who was it who said that?
Yeah.
Oh, yeah, Jasper did. So, yes, we're all very sad about Arecibo. And if you don't know what Arecibo is, Arecibo was a radio telescope. Just like we have telescopes that can focus light, there are large telescopes that are able to focus radio waves. And we're able to learn a lot by focusing radio waves, mostly learning about X-ray and other types of energy that is emitted from distant galaxies. The Arecibo antenna was particularly special because not only was it a receiver, but it was also a transmitter, and it was able to engage in something called radar astronomy, where it would send radio signals to distant bodies, mostly like minor planets, and receive the signal back and be able to determine not only details about the orbit of that body, but also details about its shape. So you could see this big structure that is this big receiver that was added to the telescope, I think a couple of decades ago. And in order to accommodate the additional weight of that receiver, they strung additional wire, additional cable to hold it up.
And that thing has to move around a little bit.
And it moves
too,
around a little bit to
over the
focus.
dish.
That's right. And what happened is that some of the cable that was used for this addition was not really up to standard. It began to fray. And once that happened, it started to kind of fall apart. You could see that a piece of it fell. Rather, a cable snapped, a piece of it fell and tore a hole in the bottom of it. And from that moment on, nobody was allowed onto the site. They said, there's no way we're going to be able to safely repair this because another cable may snap at any given moment. And instead, they flew drones around it to observe it. They had cameras set up to observe it. And what I want to do now is show a video of what happened. And hold on here. I gotta stop, pause this. Hold on. Let me share my screen again. Oops. Share screen, optimize for video.
Make sure to click the button for the sound too.
Yeah, I did, and now I gotta find, here it is. Okay, so this is a National Science Foundation video, so we're allowed to show it without copyright violations. And yeah, just wait a few seconds here, and this was kind of all she wrote. A spectacular ending. Sadly, I don't think there's going to be any plan to rebuild.
No. National Science
Arecibo,
Foundation
and
the National Science Foundation has already said they're not going to rebuild it.
Yeah. So there is a similar instrument in terms of being able to receive data in China, and that's a pretty fabulous instrument as well. But unlike Arecibo, it's not a transmitter. The one last thing I want to show you is what kinds of things Arecibo would actually transmit. One of the things, maybe this wasn't a very good idea to transmit it because we don't know what people will think of us, was that. And they, Arecibo is one of those locations where we were sending information about us into deep space. Now, not everybody thinks that's a particularly good idea, but in any case, it's too late. It's out there. It's on its way to what, M77 now, and
it's
got
about 60 million years to get there.
The M77s will receive that in some 60 million years from now. And,
they're all
going come pay a visit.
Yeah, and they're all going to wonder why it is that humans look like little stick figures.
That's right. Yeah.
Okay.
So anyway, yes, we're very sad about Arecibo.
Well, I think that's about it.
Yeah.
That's
we're probably my. Hold on for a second. I got my sound. Sorry here. There we go.
All right. So
sorry about that.
We want to thank everybody for tuning in tonight. We'll do it somehow again next week at 9 o'clock, even if we have to do it from home. But we will show pictures and we'll talk about them. And we want to, again, remind everybody about those donation buttons on the Chabot Facebook page and on the Chabot website. And again, remind you about if you sign up for a Chabot membership between now and the end of the month, you will also coincidentally be buying a membership for a local teacher. So we want to encourage you to do that if you're not already a member. All right. And with that, I think it's time to say goodnight.
Okay.
All right. Good night, everyone. You have a good weekend and a good week coming up. So we'll see you next time.
All right, bye.